So welcome everybody to our roughly monthly APSD Bio Engagement Committee online meetups. We try to find different themes each month to engage the community. If you are not aware of these already, let me just show you how to find out about upcoming events, although right now the information is fairly limited about our upcoming events. But if you go to the Division of Biological Physics homepage on APS and you click on this workshops and networking button, then you can see the various events. So we have a number of events planned for the coming year, but they're still in the planning stages. The next month's one will be for people at PUIs, and I'll turn the floor over very briefly in just a moment to Oren Schindel to tell us a little more about that. If you missed any of the past events, we've had a few about teaching over the last year. You can click on the link and find a recording of the event and view it so you can get more information that way. So hopefully you'll be able to join us for more events. And Oren, would you like to just say a couple of words about next month's event?
Sure. Thanks so much, Nancy. I'm Oren Schindel. I'm at Trinity University, which is an undergraduate institution in San Antonio, Texas. And the next event is going to be aimed at other biophysics faculty who are at primarily undergraduate institutions, with the idea that we might talk about how to help build a more cohesive national network among undergraduate faculty in biophysics. So there will be more details posted as that event materializes. And if any folks have ideas for that kind of thing, please feel free to let me know. I'd be happy to take it into account.
Excellent. Thanks, Oren. And yeah, if anyone has ideas about future themes for future events, just reach out to us and we can see if we can make it happen. So with that background, let's switch to today's theme, which is teaching biological physics or biophysics. We will choose which of those two phrases we prefer to use. Sarah Marzin from Claremont Colleges was the coordinator of this session and unfortunately was not able to join us for moderating, so I'm stepping in. And so I will start things off with what she told me she asked of the panelists. And so what we'd like to hear, we have three panelists today: Raghu Parthasarathy, who's at University of Oregon, Josh Shaevitz, who's at Princeton, and Jané Kondev, who's at Brandeis. And they're each gonna take a few minutes to tell us about their philosophy to teaching biophysics, or approach, or learning objectives, or aims when they teach such a course. You guys could each decide what you want to focus on. And then once you've thought about what you're wanting to do, how do you accomplish that? And what are the challenges, approaches, etc. So share your thoughts with us. And then after each of them have shared their thoughts, then we'll have chance for question and answer, comment, discussion from others to share your own thoughts and so on. And we have until 2 p.m. here on the West Coast scheduled for this. So I'm just going to ask you in the order in which you popped up on the Zoom and on my screen. So I'll start with Raghu.
Cool. Yeah, thanks, Nancy, and thanks for putting this together. And yeah, thanks everybody for showing up. It's nice to see several familiar faces and or names for the black squares, and good to meet all the rest of you. Yeah, so before most people showed up, Josh especially, we were all expressing shock with the term philosophy because we don't quite know what or at least I don't quite know what my philosophy for teaching biophysics is. But actually, I'll give it a slight bit of background first. I'm a physics professor at the University of Oregon, and I've taught biophysics actually in a few different contexts. I have taught a graduate biophysics course that actually this coming year I'll be turning into a joint graduate and undergraduate biophysics course, which I'm happy to chat about. I've incorporated biophysical things into an undergrad stat mech course, which I think is a really great thing to do, both for biophysics, but especially actually just for learning stat mech. But then probably my biggest kind of emphasis is actually teaching biophysics to non-science majors. So I created and I've taught several times a physics of life course that's intended for non-science major undergraduates. So it's one of these courses that satisfies a general education science requirement. And that's been a lot of fun and slightly related to that, but not exactly. I also wrote like a popular science book on biophysics and biological physics that was quite a nice experience to do. But especially in the context, I think most of my efforts have gone towards teaching biophysics to non-science majors. And there's sort of a couple of different goals and a couple of different strategies. And maybe I'll come to the strategy part later after other people talk a bit as well. But I have a variety of goals. One of them is really just to convey the beauty of this field, biophysics, especially given that its very existence isn't really known to many people. The fact that there is an intersection between biology and physics, is news. But the other thing that's really kind of great from the perspective of, I think, a non-scientist is that just a little bit of information or skills related to like biology and physics and knowing a little bit about numbers and not being very advanced in any of those things gives a really remarkable ability to make sense of a lot of things in the world. You can do very elementary introductions of concepts like surface tension, and that can explain things like, why you make surfactants in your lungs and how that makes it easier to breathe, and how premature infants, until very recently, the last few decades, would quite commonly die due to a lack of these lung surfactants and an inability to combat just sort of the physical forces associated with like liquid surfaces. So there's this kind of amazing, just not just phenomena at the intersection of biology and physics, but even knowing a little bit about them actually makes sense of a lot of phenomena that are really kind of, I think, eye-opening to students. And so that's, both interesting and I think very kind of liberating in a way. There's a sense, especially among non-scientists, that one has to know a lot of either, to them, painful math or complicated details to say kind of things that are relevant to them about, their premature siblings and stuff like that. But I try to convey that there's a lot of very real world things that you can get at with a kind of a minimum of depth. Yeah, so I'll leave it at that, and I'm happy to comment more afterwards.
Great, thank you, Raghu. All right, so let's hear from Josh.
Okay, so I'm Josh Shaevitz. I'm at Princeton. I'm also chair of DBio, so thank you for coming to this meeting. If you went to a previous one of these, you may have heard from my colleague Bill Bialik about teaching, and he and I teach a number of things at Princeton both together, and then we have some sort of orthogonal courses. So I'll try to give you a sense of my version of things and the things that we do a little bit different. There are kind of three contexts in which I teach biological physics, mostly every year. We have an introductory course called Integrated Science, which some of you may have heard about. I've talked about it at the March meeting sometimes. It's sort of an honors immersion science course for advanced honors students that tries to do all the sciences together. And I've always viewed biological physics as one of the key places where we can link lots of threads together for the students. This is both in terms of sort of lecture material, picking problems in biology that allow us then to discuss lots of interesting topics in other fields, including physics. Also in the laboratory. So for example, one of the laboratories we built is the students build a spectrophotometer and then measure growth curves of bacteria. So it sort of, shows them how you can bring all these skills together. And then another area, which I'll probably talk about several times today, is that we try to give the students at a younger point than they would normally see it more advanced concepts in statistical mechanics, optics, and some of the other physics fields that seem particularly, let's say, more relevant for biology than maybe projectile motion, which we do some of, or orbital motion of the planets and things, which maybe those particular topics are not so relevant for what you need to understand biology. So that's a freshman course. It's not a biological physics course, but it has a lot of that material in it. Then I have taught for many years. It was gone for a bit, but it's back. An undergraduate course in biophysics. This is an orthogonal option to Bialik's graduate course, which is what that book, Principles of Something, is based on, which many of you may have. So we have an undergraduate course, which is quite a different course. It's more of a survey course of lots of topics in biology, in biological physics. I have many goals with this course, and I've sort of mapped out ways of doing it. One is to point out that there's really, new physics in the phenomena of life, and to challenge the students. So it's geared towards upper level physics major undergraduates who mostly come in thinking that they must know all the physics already, and there's nothing biology has that would challenge anything they've ever seen in terms of physics. So I try to find areas, non-equilibrium phenomena, et cetera, things that really challenge their view of things. They haven't really gotten to advanced stat mech, phase transitions, any of that stuff, right? So basically their version of stat mech is static and not dynamic. And so there's lots in biology to show them that, there's more to do. It's also an excuse for me to teach areas of physics that are no longer in physics departments: solid mechanics, fluid mechanics, polymer dynamics, all of these things that were at one point physics and have now moved to engineering. And our physics majors, certainly at Princeton, just don't even know these exist. They could not tell you how a beam bends. I mean, very basic things, right? It's not in the intro course, and it's definitely not in their advanced courses, which move very quickly into quantum and cosmology and exciting areas of physics. But I think biophysics or biological physics is a nice place to teach some of these concepts. You can't do a full course, obviously, but you can introduce aspects of it. And I found that pretty successful. Like soft matter, biological physics is a place to introduce stat mech without H-bar, which I think conceptually is the best way to understand statistical mechanics. You understand why we conventionally talk about lasers and two-level systems for various reasons. But, I think it hides, when you only do that, it hides some of the beauty of statistical mechanics. And then the last thing that I wrote down that I found to be a real feature is, unlike essentially anything you learn as an undergrad in physics, the primary literature in much of biophysics is approachable to undergrads. It's not too deep. It's written in English. It was probably written in the last maybe 50 years. I mean, there's obviously older examples, but there's a lot of it that you can assign as primary literature, which is something that happens in the biology departments at our universities. The undergrads learn how to read papers. In the physics departments, they do not learn this, because frankly, you're not going to go read Maxwell and Newton. That is not the way you should be learning those subjects. But with biological physics, you can introduce primary literature. And I always found that to be a nice exercise. And the students come out quite a bit stronger in terms of reading these things. We also teach a 2-week summer school called the Physics of Life at Princeton. It's a version of all of this stuff. I don't think there's anything kind of to add to that. It's a fun experience, but it's a whirlwind 2-week kind of a thing. So I don't know. Those are the sorts of things that I've been doing.
Great. Thanks very much, Josh. All right, Jané.
Yeah, thanks again for organizing this. I always find it very sort of inspiring to talk about teaching, and often even more so than about our science. But I think a lot of the sort of themes that I was going to bring up have already been mentioned. So maybe I'll try to just bring up a couple of things that are maybe slightly orthogonal to what we've heard so far. So I'm Jané Kondev, as Nancy said, and I teach at Brandeis. And actually, for the past almost 10 years, I've been exclusively teaching sort of biological physics, but as a first-year undergraduate course, so a course that's taken by freshmen, first-year undergraduate students, and it's got, it has some elements of this sort of integrated course that they have at Princeton, but it's not really that, because it's a regular course, meaning it doesn't really it meets twice a week like any other course, and it doesn't substitute for any of the science course. But what it does do, it brings together first-year students who, they don't really know at that point what they're going to be doing in college. A number of them often think they're going to go to med school. One of the hidden agendas is to tell them maybe med school isn't for you if you really like research. So that tends to be successful, depending on who you ask. I've had some actually angry emails from parents about that. So maybe they did not see that as a success, even though I did. But the key thing that this course, and sort of it's a biological physics course to the extent that the point of the course is to study sort of very modern problems in biology, literally things that are hot off the press. As Josh just said, we tend to read primary literature, often things that have been published actually in the last 5 years, not even 50 years. And my main goal is to kind of show these students that all the science that they've learned in high school and the mathematics they learn in high school, that they're all really about the same thing. They're about our attempt to describe nature in some way that allows us to control nature. And the goal is to give them, use biological physics to give them this sort of sense of all these different sciences, physics, chemistry, biology, mathematics, being all about one and the same thing, that they're not living in these silos as they're often presented, both sort of to these students in high school, but also when they get to college. So that's one of the key ideas, and and that's one of the key goals. And the other one is to sort of teach them about science as puzzles. So this is something that's just sort of something that's very dear to me. The reason I got into science is I always thought it had the best puzzles, at least the best ones I heard of. And so that's sort of the approach. So when to just be concrete. So for example, this year, every year we do something different often, but this year we started with the puzzle of how does a cell control its size. And so, so what's interesting about the puzzle is that it takes a little while to get to the point where you can convince the students that this is a puzzle, because when you first sort of state the problem or talk about it, they just kind of think, well, a cell, it knows, they give cells these sort of very anthropomorphic abilities to know about their size and to be able to measure themselves and so on. But I try to get them to kind of, we try to come up with ideas. Well, how does a unicellular organism, which to some approximation is a bag of chemicals, how can it measure its size and figure out when to divide? And so beyond discussion, I'll introduce them to some like very simple models. For example, a lot of fun is to talk about something called the timer model, which is the idea that a cell grows and keeps track of time, and then when the time reaches the doubling time, they divide. And then we'll write some simple, for example, code to explore this model. And it seems to work, except once you decide that maybe, well, this clock, if it indeed exists in a cell, cannot be perfect. So if we add a little bit of noise, they quickly see through experimentation with their code that this leads to kind of uncontrolled drift of the size of the cell. Both they can become too large and too small. And that's probably one of my favorite points in that unit that we do in the course, when they sort of see on their screens. I don't tell them what to expect, but the idea is for them to be puzzled, to see that there's something going on here that doesn't make quite sense or doesn't jibe with their initial intuition. And most of the time their initial intuition is, well, if you wait till you double and you divide at that point, if the clock is a bit off, why should that matter? And they quickly see that that's not the case, and that gets us into discussions of, well, what might be a good way to regulate size. And then we go into the primary literature and look at some experiments and try to compare it to some other simple models like the adder. And so the course is broken up into these kind of units, which bring up biology and math and physics. As I think Josh mentioned earlier, it's also sort of, allows me to kind of introduce these students very early on to ideas from probability and statistics, something they normally wouldn't hear until much later. But again, and that's the thing I sort of kind of want to put out there for discussion is, I feel like what I see as the greatest benefit often of this course is to give these students a sense that that the science they're learning, the stuff they're reading in these books, that they can that stuff is actually very much alive, not in the sort of alive biology sense, but alive in the sense that this knowledge is useful, that it's actually practical, that they can apply it to try to figure out sort of puzzles that are out there. And biological physics is cool because it offers some puzzles which actually they can tackle. I mean, understanding, sort of, I don't know, something about dark energy in the universe that I think I would have a hard time getting to that question over a semester with with 20 or so undergraduates, which is kind of this class that I teach. So that's sort of that's my take on it. And then for those of you who might be interested, this course actually has 2 parts, and in the spring semester, it's actually turns into a lab course, but not one where the students do experiments in a lab, as sort of that's been designated for the course, but they actually go into research labs in groups of 2, where they're paired up with graduate students who I helped train over the fall semester. And with the help of these graduate students, they each pair completes a project over the spring semester, and then at the end of that semester, we have a poster presentation and so forth. So so again, this sort of is all done in this context of getting them to sort of appreciate that science is about puzzles, that they can do science, and that a lot of the fun in science is in the doing of it. So I'll stop there.
Great. Thank you very much, all of you, for sharing some information about the courses you teach and some of what you aim to get out of it, and you hope the students get out of it. And thank you to everyone else who's been here, who's been putting up introductions in the chat. It's really nice to see where people are coming from, and it's really a wide range of different courses that I think are represented by the people in attendance as well. So at this point, we'll open it up for discussion and Q&A. So if you have a question and you want to ask it yourself, put up your hand in Zoom and I'll call on you. And if you don't have access to a microphone or prefer to have the question read, you can type into the chat and we will go from there. Maybe I will get things started. I know you each mentioned sort of introductory courses, but also more advanced courses that could be offered, and Josh talked about one that's predominantly physics majors. I'm curious whether in any of your departments of physics, biological physics is a required course, or if there's ever been any discussion in your departments about making it a required course for physics majors, that is.
Not in ours.
Or in anyone's department on the.
In anyone's department here.
I mean,
Like-
ours satisfies a requirement, an elective requirement, the same as all the other subfields. Like, I don't think we have any subfields of current modern research in physics that are required for the students. The requirements are, STAMEC, E&M, quantum, etc. And then there's a long list of electives for which you have to select things. Atomic physics is in there, and so is biological physics.
Yeah, for us, definitely not required. Yeah, it sounds very far-fetched even to contemplate. Yeah, definitely not required. And in fact, even we have had like an upper division biological physics course kind of sporadically offered, but there's actually not been really that much enrollment in it. And actually one of my motivations for making my graduate biophysics course a joint undergraduate graduate one is to deal with that issue.
Daniel.
Yeah, on this question about requirements, so most physics departments seem to still require upper level mechanics of Lagrangian Hamiltonian mechanics and upper level E&M, which is basically applied math that cover the kind the computers are really good at. So it seems to me when being somehow collectively defeatist, if not trying to push to get some kind of biological physics required. I mean, I also think all departments should do a back of the envelope physics class, but it's required. I mean, most places do it, but they require that. And actually, the doing that can be in different flavors, including an astrophysics flavor and the biophysics flavor. And so that there's one way to possibly get it in. But I'm certainly feeling that the physics curricula are incredibly old-fashioned almost everywhere, and that really trying to say what does one drop is crucial for trying to think of what to add, and that's always very hard. But
Yeah.
needed.
Jané.
No, just to Daniel's point, and So and also to Josh's, so you know, like in Princeton and like most other places, biological physics is now, you know, is one of the sort of electives, just like you know, astrophysics or condensed matter physics, particle physics. These are all electives. And I don't know if this thinking is common or not, but sort of one way that we've thought about it for sure is that the things that we require, for better word, are methodological courses. So we see like stat mech and quantum as methodological courses, meaning like in some sense these are, you know, in some ways, as Daniel also said, these are courses where you learn the math methods or the experimental methods, and then, you know, then these other sort of courses like astro and bio, there should be more about phenomenology and also applying these methods. So it seems if people buy into this kind of thinking and maybe not, but if we take this as the assumption, then I think the question is not so much can we make biological physics required, but can we think of what is the foundational courses that actually you would want a student who's interested in biology and biological physics, which ones you'd like to take, you know, them to take, and kind of the obvious one is stat mech. And so maybe the real discussion is like, how do we get students to be taking thermal and statistical physics before their senior year, which at least at Brandeis is usually when physics students take this, because, you know, some crazy, you know, view from the 60s, and from what I gather, it has to do with Kittel's book. And Kittel himself seems to have decided that we all need to know quantum mechanics before we can do stat mech, because somehow, you know, you can only count states if they're discrete. So it seems to me like this, from what I've sort of
and we often
I've been
teaching
engaged
the
with,
thermo.
this is the problem we have to deal with. Sorry, Daniel.
We often drop teaching the thermo and just teach stat mech now.
Yeah.
So it's, you know.
Yeah, because, you know, why bother with thermo? It's antiquated and it's useless. You know, you can derive free energies from counting. So I mean, I'm of course being, you know, sarcastic here. It's crazy that we've adopted this kind of view, in my opinion, and it's actually interesting. I think someone should sit down and do a proper job and try to understand why is it that we teach undergraduate physics the way we do. I did try a little bit of that, and it looked like most other things in science in this country, it has to do with the Sputnik in the late 50s, early 60s, when at least I found a couple of sort of sources of this where teaching of physics was changed dramatically because there was a sense that we were lagging behind the Soviets. So if that's really why we have this curriculum, I'd like to see it dropped or revised at least.
We do have something similar to what Daniel was saying. So a few years ago, one of our particle phenomenologists introduced a first-year kind of data analysis, data introduction to particle physics, where they analyze data of different kinds. And so, you know, they don't learn any of the theory behind it, but it's a way of getting the data, getting them into the modern questions.
Yeah.
And so we're introducing a biophysics version of that next year or the year after. Is the plan. So that's similar to this idea that you could have these entryways into the department to get you excited before you have the official tools that allow you to derive things and stuff like that.
Great.
Yeah, that's a very interesting, Josh, because it seems like, you know, and I'm a big supporter of that. It's like inverting the pyramid. Let's get the students first excited about phenomena and puzzles, and then they could choose what, you know, in the later years, what tools they need, you know. So if they're excited about, you know, particle physics, you know, let's take a bunch of quantum and get to field theory maybe as soon as you can. But if, you know, living things excite you, then, you know, try to get, you know, in your sophomore year as soon as possible, some thermodynamics and some, you know, continuum mechanics and all these other things that you described. So I think that's a really interesting idea.
Mm-hmm. All right, Raghu, your hand went up, and then Don, do you have something to add before we move on to the next?
I'll leave it. I do have a question, but I get to speak enough, so I'll silence myself for a little bit. Take a question from the audience.
All right, Patricia.
Okay, so I have a question that actually I do not know whether I like the question or not, but I have to make it. And I want to know what the panelists think about standardization of the content of biological physics courses, because I am fascinated with what each of you does, but I think it's different. and each of you may require different textbooks, resources, and then if we want to replicate your experiment, adapt and adopt, then how can we do that, right? So it's a question is about standardization and teaching resources for the rest of us.
All right, who wants to tackle that one first?
Two of us wrote a book or wrote books. So not me, the other two.
All right, Raghu.
I guess I could comment a little bit. So yeah, it's a really interesting question. There is, I think one thing probably a lot of us have noticed if we teach biophysics is it's a very, it's a all of us who are biophysicists know it's a gigantic subject, and you certainly can't put all sorts of topic, you can't put every topic into a course, nor should you try. But I don't think it really calls for sort of a standardization of topics, because I think one thing that I think all of us agree, and that is reflected in like the sort of big three upper level like biophysics books, like Jané and Rob Phillips's and Bill Nelson's and Bill Bialik's, is that there's differences in the particular subjects, the particular topics being looked at, but a lot of the broader goals of how do you apply statistical and probabilistic reasoning to these systems? How do you kind of get things from like contemporary literature and kind of know enough of the language to be able to like interpret that? They're actually remarkably consistent throughout all of these. So I think even without trying to standardize things, there is actually a very unified approach to all of these different biophysics sort of books, and probably many of our courses as well. So I'm not terribly worried whether, in course A, they happen to cover like DNA mechanics, and in course B, and not membrane mechanics, and in course B, membrane mechanics and not DNA. I think those are, yeah, I'm not terribly worried about that.
Jané, would you like to add anything?
Yeah, no, I appreciate that, having sort of material out there, and especially textbooks that are sort of that exist at different levels, and and the thing that this book I've been part of was never originally intended to be a textbook, even though it's used for that purpose by some people. I don't, anyway, so I think they're really good sort of materials for upper level courses, where I think we don't really have, to my knowledge, things that I would find sort of useful or good in some, or things I would want to build a course around. They're kind of more at the introductory, so like first year, second year level, and so in my mind, this is where the real problem's at. Not so much because I think if the goal is to teach biological physics in a senior kind of to bunch of physics seniors, as a sort of kind of the typical thing that people do as an elective on par with like particle physics or condensed matter physics, if I were doing it, I'd probably take one of these, a newer version of Phil Nelson's book probably is the one I would pick. It's nice and small and covers a bunch of really cool topics. I forget what it's called. Not the old one, but this newer one, something about life and physics and so forth.
Physical models of this physical models one.
Yeah, something like that. Yeah. So I'm a fan of that one, for example, for like if I were teaching a senior course. But but I think the real problem is how to get students excited about these things, very earlier on, and how to get them exposed, how to break this sort of monopoly or whatever, this very traditional sort of this very, very traditional thing we have in physics, where you take classical mechanics, then you go on and take E&M, and then you go quantum mechanics, and that's basically your first 2.5, maybe even 3 years of your undergraduate education, which I know for a fact now that I have a 19-year-old who's in college who is excited about science, and I speak to him and a lot of his friends that they all decide they don't want to do physics because it's too rigid. They don't want to follow this. They want to try out different things. They're often taking like applied math instead because it offers them opportunities to quickly get into things that are sort of modern and exciting and so forth. So to me, that's like the bigger problem. And for that, we need to, if we're going to kind of try to get us away from this very rigid curriculum, then I think we are missing some I think we're missing good textbooks that will allow us to do that on a grander scale, so that we're not each one of us individually, as was mentioned, reinventing the wheel, right? So I'm afraid.
So I think so there's two aspects to this question. One is about sort of standardization and whether we can all agree on some grand curriculum, maybe with levels or something like that. And one thing I would point out, so I mean, part of this discussion was about how we don't like that physics is stuck in this rigid curriculum. But I know on the other side, my biology colleagues, at least at Princeton, have been complaining since I started that there is no canon to them in biology. They don't know what to teach. It keeps changing. It's so, they don't, everything changes so fast, et cetera. There are these big textbooks, right? But they're essentially out of date the minute they're published and all this sort of stuff. And so they always long to have this very standardized thing that we have, which we're now complaining is too rigid. I think it's a little complicated. For you specifically, Patricia, and for others, like, one thing that I always did was send my notes around. So MIT taught a version of my undergrad biophysics course for a while. I mean, it wasn't exactly it, but they had my notes and they would appear back to me at some, in funny ways. I know Bill's book was like a PDF long before it was really a textbook, and it was being used, parts of it were being used. The community, I think, is very willing to share these resources. So we could either on an individual level or maybe even collectively collect these sorts of teaching resources. We never made integrated into a book. I'm not a book writing person. I thought about it once. It is not my calling in life. I don't have the patience for this. But it doesn't mean that we can't collect.
You can do it.
It just doesn't mean you can't collect lecture notes, right? I have lots of lecture notes, and they're, some of them are quite good because I give them out. I make them look nice and type them up sometimes and things like that. So, maybe we should think about collecting teaching resources that aren't published or publishable, but as a resource, even through our DBio, our division, that could be useful for people.
Great suggestion, Chair of DBio. Daniel, you had your hand up next.
Actually, Josh, about the collecting information, that was something maybe one could try to get some APS people involved to help on that, because I think it's really useful, even if it's just syllabi. It can really be useful if one's trying to do something, or then who to talk to and trying to get more information. So I think that is very valuable. Just on the one thing, when I get to Jané, and several of you are sort of trying to do this, but it seems to me one of the really missing things is the class where you say the sort of goal is the students who come into college as physics, math majors, or whatever, having been turned off biology in 10th grade. And then end up later on professors in departments with bio in the title after they rediscovered biology as a graduate student, and that somehow getting them, exposed to exciting biology as fast as possible in a taught in a way that people who are mathematically inclined and don't want to memorize a lot of facts can appreciate. I tend to find a lot of the biophysics things much too sort of static and statistical mechanics and things focused, rather than just from the beginning talking about dynamics. And that's of course also true with a lot of the physics curriculum, right? I mean, thermodynamics is called dynamics, but one does all basically the static things. And you can do thermodynamics in the context of molecular and cell biology in really nice phenomenological ways, sort of paralleling how it's done for using engineering as a sort of motivating force, and really get into the dynamics and everything right away. But I've tried several courses on that, I think without much success. But I sort of feel there ought to be more in that direction, much more dynamic focus. And then you can start right at the beginning. You say, okay, we're going to consider biological functions and not talk about the approaching it as coming from physics, But and Mahadavan was one who I think persuaded me of this. And one should teach a lot of biology like engineering. Is you really say there are things that biology does, and then talk about how it does them. And then of course that leads you to have to introduce various things from physics and things as well. But I think it's a sort of quite different motivational a beginning point that I find is at least fun to do. I don't know how it works with the students really.
Great suggestions. Since I don't think there was a specific question, I'll go and we'll hear from Laura, who also has her hand up.
Yeah, I wanted to say that the idea of having a kind of I share the repository of notes. It will be a great resource also to to cater to something more spontaneous and more quickly evolvable in terms of teaching classes that are literature based or experiment based or topic based, where you select and maybe you select the topic or the function, as Daniel was saying, depending on what is more interesting to you at the moment or is considered interesting by the community at the moment, and then have maybe not necessarily a textbook, but these notes that you can draw from to then guide discussions. So I think that's a great idea.
Great, thanks, Laura. David.
I'll just chime in to say that I'm also very supportive of these ideas. I'll mention that I've benefited a lot from Raghu's course notes in biophysics, and there's sort of an equity aspect that I knew Raghu, and so in talking, it came up that he teaches this course, and I was like, oh my God, I'm going to teach biophysics in a year. Can I please borrow your notes? But there are many people who don't have those kinds of professional networks that would really benefit from this kind of thing. I've been involved in a fairly unsuccessful attempt to do a similar thing with StatMech. And there are various complications that arise, things like copyright, right? Of kind of, sharing and people who one day dream of writing a book, but it hasn't risen to that level, and do they want to share? But I think it's the kind of thing that I could imagine with more institutional support could be very successful. So I'd be a fan of that.
Great. I think there's a lot of interest in this, but concerns, as you say. There's also been a number of points in the chat, which are great for all of us who are here now to read. But if there's any points that anyone has made in the chat that one wishes to share now with everybody as well, then it will go into the recording. Now is your opportunity to do so.
Sorry, Nancy, is the chat going into the recording or wherever one links
No.
to?
No, I mean, I think it gets saved, but I think when the APS uploads the video to YouTube, it's just the video. So comments that have come in the chat are something we're reading, but I mean, I can read them out, but anyway, I think it's just nicer if people want to share them for posterity to do so. And if not, yes, Jané.
Oh, I think because I think I saw in the chat that Raghu said that they have successfully managed to get StatMech being taught in the second year. So I'd love to hear about those experiences, because to me it seems like that could be a really good way, and I'd like to hear how to really good way to introduce students early on to biological physics because if we teach, it's like you teach E&M and the examples are often, well, I don't even know what the examples are anymore. They're usually these silly things like spherical something or other next to spherical something or other. But in teaching StatMech, I mean, if we could, I could see easily how that could be sort of that there could be a lot of biological physics infiltration in a course like that if you're teaching it to us like a a sophomore class. Anyway, so just curious what the experiences were at Oregon with that.
Yeah, so I actually don't know the history, and I don't know if it was very deliberately thought out. So, I've been here since 2006, and since long before I arrived, it just happens to be how it was. There's the standard first year physics sequence, and then the second year one. The first term of it was always a weird hodgepodge of relativity and things like that. And then the second two terms were stat mech and thermodynamics, whose content depended a lot on who taught it. I'm actually teaching the final term of that this term. So it's just always been the case here that that's how it's been. And it's certainly considered, I think, a difficult course for the students because it is really, whatever course they take after their first year sequence is, I think, a big shock in like difficulty and like abstraction and just like, being less formulaic, whether it's quantum mechanics or stat mech or whatever. So it is considered, I think, by many of the students rather difficult. But in terms of, doing stat mech without having, quantum mechanics and so on, that just is not an issue. They, first of all, have seen kind of the baby version of stat mech in some aspect of the first year or the first year plus a quarter. So the idea that there are particles in a box with energy levels and stuff like that is not completely new to them. And we just point out, okay, you'll learn more about how one calculates these sort of states and so on later, but let's just take as a given that these exist. And that's fine. That's not even close to a stumbling block in a course like this. So it's very doable. Interestingly, for me, actually, even as someone teaching it, it didn't seem so weird because this is quite a while ago, but I was an undergrad at Berkeley, where after the introductory 3-semester sequence, you could take any of the upper level courses in whatever order you wanted, which I think is the ideal scenario. So I ended up taking stat mech as my first like upper level course, and again, you take some things on faith and go from there. So I think it's very doable. I think having been through sort of discussions like this, making the argument that one ordering is better than another is just a never-ending debate that one should try to avoid. I think the argument to make is having everything beyond introductory things be put into any sequence that one wants, which also gives students more flexibility in like their schedules and stuff like that. Yeah, so those are my 2 cents. I'm curious if somebody answers the excellent question put up in chat about introducing biophysics to students from a biology background. If nobody comes back to it, I'd like to comment on that one.
Yeah, so I think that was the next question before the hands that are currently raised, and we are getting closer to the end of the time that we scheduled for this. But yeah, so any thoughts on introducing biophysics to students from a biology background? And maybe can I, as a moderator, jump in as well, because we have an undergraduate course here at Simon Fraser University in Introduction to Biological Physics, and the prerequisites for that are pretty minimal. They're first year physics and first year calculus. We used to have a first year biology, but we found that led to very few students from physics taking the course, and so we removed that. And actually, it's been really great to have a mix of people in the class. I think it was Raghu who commented that your course didn't have very high enrollment as an undergrad only course. And so I found that in having students from all different departments, it boosts the enrollment, and it's now one of our more popular third year level courses. But it requires careful planning because you can't get into very advanced physics and you can't expect too much in the way of a biology background. But yeah, maybe I will see if any of the panelists, and maybe particularly Josh, because we haven't heard from you recently, want to comment on answering this question.
I give
And if you
lectures
don't,
in random biology courses sometimes, but I've never done anything systematic. I talk about optics. I have a microscopy thing I can do of various lengths that works well with non-physics students, but I haven't gone any deeper than that.
Okay. Jané, yeah. You're
on
muted.
mute.
Sorry about that. And I was just saying, most of my students plan on being biology majors actually when they come to my first year course. And I guess if I have anything to say about it, and I've taught biologists physics at every level, I guess, including PhDs and postdocs at the marine biology lab. And I mean, I guess my only comment would be the sooner you get them, the easier it is, because if you get a first year student who plans on doing biology, they actually know quite a bit of mathematics and physics from high school. By the time they get to be seniors, which I've also taught, maybe biology seniors teaching them physics, they've forgotten everything. So they've, you have, it's often a struggle to multiply numbers in scientific notation, and they're doing great in biology. So yeah, I guess that would be my, to me, it's why I've loved, I can't seem to give it up teaching these first year undergraduates, because they have no fear. They haven't been told that, the gene rules supreme in molecular biology and you don't really need to worry about anything else by anyone yet. So you have you get a chance to kind of show them that actually the mathematics they've learned in high school can be put to really good use to understand all sorts of cool things in cells and real living, things, kind of problems.
Yeah. Okay, Raghu, did you want to add anything?
I'll just briefly add. So with my graduate biophysics course, I've had a few non-physics students from like biology and chemistry, which has been fantastic. Having them in the class and getting like those perspectives on topics. The big challenge and the limitation for getting more, especially biology students, has been math background. And I've been told by many students that they would like to take the course, but they probably can't. And then I actually had one biology PhD student in the course who I realized like a week in had never taken calculus. And that was rather a shock. And it took some thinking, what are we going to do with you? And I haven't really solved this question, because I'll be teaching this, as a joint course in fall, and I've been thinking a lot that I really need to kind of almost make it 2 parallel courses, but that takes a lot of effort.
Mm-hmm. Had they had any programming experience?
Yes, that's what saved him. So he actually had a
you
decent
can get around
grasp.
calculus with numerics.
Yes. Yeah, so there were a bunch of things where I had them do, calculus of various sorts, and I sort of let him program his way around those. So it worked out, but it took some effort.
Cool. All right, David, you had your hand up next.
Mine's a reversion to a previous point. So if Laura has something related to this, I'm happy to yield the floor. No? Okay. Just a follow-up comment on the idea of sort of sharing materials. I mean, we talked explicitly about sort of biophysics courses, but as has been alluded to, many of us teach other courses where it would be nice to have more bio content and more bio applications. And so I think there probably would be a big interest in sharing materials related to classical mechanics problems that, as we said, are not inclined plane, but are more bio-oriented, or, StatMech applications that are not BECs, so that we can kind of import more bio content easily into courses that maybe exist and have been written, and designed by people coming from more hard condensed matter backgrounds. And so I think that would be another area where sharing of materials could be a great benefit to the community.
Are there any ideas about how this could happen? I know we saw in the chat the Physics of Life portal, which has been focused on collecting things for teaching physics to life science students, but does anyone, whether a panelist or not in attendance, know of any successful ways that have been developed to share materials for courses, or could serve as a model of something we could try?
My experience was just in other realms, particularly StatMech, was just that you really need some sort of institutional support site, et cetera, because if it's kind of self-organized, people get busy, maybe no one's teaching next semester, and so everything goes silent, and next thing you know, everyone's forgotten about it, and that's it. And so something where it's a little bit more of a permanent home and maybe easier to build up a critical mass rather than word of mouth might be helpful.
Yeah.
Are any of you familiar with this? I don't know about this portal. I've just opened it. Who runs it? Who funds it, etc.? the Living Physics portal? Anyone know?
So it's primarily sort of been something, it's been a my sort of knowledge of it is it's thing that the American Association of Physics Teachers has been sort of backing for a number of years, actually at least a decade now. There's been a very long standing discussion in the American Association of Physics Teachers, including conferences and such, about how to properly teach physics to life science students, with the understanding that we on average do a really bad job of that. And so that's where it came from. But at least there was one meeting recently in DC that I was part of, where we've been discussing about expanding this portal to cover also biological physics, which at the moment it doesn't really do, even though a lot of the things you'll find there, you'll see, the obvious clear overlap. There's very similar objectives there, right? Or at least overlapping ones. So I think, talking more to the APT people, and that's one thing we could do. But I think that is moving along. So hopefully, I think we also need, not many people in the biological physics community have a sense, know about this portal, like just demonstrated. So I think that's another thing that could be done. But also this, I forget who there's a number of people involved. I know Phil is one of them. This new journal, The Biophysicist, seems like a decent venue for us to all, I think, everyone needs to kind of, do the work, but I think contributing articles there about, with, people talking, if people could start contributing articles there about the things they've done to sort of add biological physics to the physics curriculum and all that, and just like the American Journal of Physics, I think for a lot of us has served as a good place to find interesting things to do in our physics courses. Maybe we could also use the biophysicists in that way to sort of promote modules that could be used in physics courses that have biological content.
So. I mean, I worry a little bit that there's definitely a barrier to producing something sort of publishable, even if it's on just the scale of a paper, like an APT kind of paper. Whereas some place where you could put, semi-raw lecture notes could be okay. I don't know. We'd have to think about it. There's certainly intellectual property issues that need to be discussed. When you teach, you can kind of steal lots of things. It's all fair game.
Half my slides don't have the proper, sort of journal references, just because I can't be bothered or I forget. And it's so putting that. So people ask me for my slides and notes, and I do get worried about, like, well, this is not quite. I mean, if it's a friend, I don't care, but just putting it out in the public could it's problematic unless it's been done properly, right? I agree.
All right. This is a super stimulating discussion. I see hands still up, but I also am cognizant of people's time and time commitments, because we have been here an hour. Our panelists, are you interested in staying for a bit longer, or shall we just cut off the discussion now and perhaps organize another event in the future, maybe around the theme of sharing teaching resources of relevance to biological physics? And
I can stay for another like 15 minutes or so. I'm really happy to do that. This is a really good conversation.
Mm-hmm. Okay, then I'm gonna just keep it going, and we at least have one person who can answer. But if people need to leave, please do. Don't feel ashamed to leave. But let's just, while everyone's here, it is a great discussion. Yes, Laura, you had your hand up, but you have dropped it down. Is that?
Yeah, I just put it in the chat, what I wanted to say.
Okay, to save the chat. Yes. So if anyone sees the resources here that they want links to, save it so that you can access them after. Daniel.
Yeah, I just wanted to come back a bit to Jané's point about the introductory courses teaching sort of methodology. I think that's one of the biggest problems. I mean, I find students come to graduate school having done undergrad in physics and don't know any of the things that I would like them to know as far as methodology. And I think the basic problem is that there isn't phenomenology taught from early on. There aren't approximations taught. There's usually the approach that here's the equations that are exact and you derive things from them. And one of the advantages of getting, especially thermo, not stat mech, but especially thermo, very early on, is it's the power of the phenomenology. And one of the nice other things about the biological examples from the beginning is none of the equations are right. And so you right away have to start talking about, what properties are there that follow from a simple dynamical system and so on. And certainly the upper level mechanics should just be thrown out entirely and replaced by, dynamical systems class, which then one can do with various motivations, because the students end up thinking the only operators that matter are Hermitian, that most problems are linear, or if they're not linear, you just have to do simulations, and how to approximate things, how to do orders of magnitude estimate, stuff like that. They have no idea, right? And so I think that one can try to make arguments. I mean, I've tried with very limited success with colleagues about that we're actually not teaching them the right ways of thinking and doing it for being physicists, as well as for what other areas they're going to do. I think the astro people probably would be maybe most amenable to that, because they sort of rely on a lot more similar things to what one does in biophysics, and practicing kinetic physicists certainly too.
Great.
Yeah, how do we go about affecting this change, right? I mean, I have this discussion now for a number of years, and I know you have, Daniel, even for many more years, and it's a little hard to figure out how to get us from here to there, right?
Yeah, I mean, the one thing which, hopefully we'll be able to do, I don't know if we will, is to do a serious biophysics option in the physics major, which starts off by dropping a lot of the now required upper level courses and puts in things instead of them, and then gives possible alternate options for the introductory courses. But we're also talking about, and actually Harvard, this was discussed seriously at one point, and was having more like a sort of a more applied physics version of the physics major too, with sort of courses that you could go back and forth from at various levels. I mean, Cornell, having both an engineering physics and a physics, has a bit of that, but and I think some other places that are both do as well. But yeah, it's an uphill battle.
Yeah,
I mean,
I think in our department, we have streams of physics. So that's the way that we've solved that problem, is so you can still do your physics major, but you could do a biological physics major, biological physics honors, chemical physics major at honors, math, physics, applied physics. And so then that's an opportunity to mix and match the courses. And then each stream, like the biological physics stream, sort of has, you take a common first 2 years, and then you kind of students choose, do they want to go more the molecular cell biology route? Do they want to go more the physics route? And so there's different streams that can prepare them for the standard graduate school in physics or anything else. So that's one way to do it when departments do not want to give up their physics core, is to just make a branch, I suppose.
Yeah, I think there's a couple potential issues. I think Raghu brought this up in the chat. I mean, in physics graduate school, we expect the incoming first years to know some set of things. And we do need to then collectively relax that if we're going to not train our undergraduates in the same way, because there's this expectation. So those kind of have to go hand in hand. I want to go back to something that I think was mentioned in the very beginning. A lot of these required courses we teach really serve, at least in part, the purpose of teaching various kinds of mathematical skills, really playing with vector calculus and E&M, right? That's probably the first place where you did a whole bunch of weird integrals in 3D and funny coordinate systems and stuff. Maybe you saw some in mechanics, but E&M. So you could imagine that we could all agree on the kinds of math formalism that we want the physics majors to know, or kind of topics to be familiar with. Dynamical systems, I agree, would be an awesome one. Various things in 3D calculus, and then pick from the various subfields interesting problems or way of using those tools, and so teaching the tools in that way. I mean, that would be a drastic thing to do. There's no way my department's going to jump at that right away. Some of you have been in my department. It is not the most liberal of physics departments in terms of education. But you could certainly imagine doing that, right? Chemical concentration, doing things of absorbing spheres. That's basically the same calculation you would do in E&M, but maybe more interesting in terms of an E. coli chemosensing, as Purcell taught us, et cetera. So I think there's a lot of room for doing very creative things like this, where the students come out with the same tools they would have had, but now having seen many more interesting, not even modern topics, but just topics in general from different sorts of fields, not just biophysics, but sort of all over the place. So I think that would be a really fun thing to think about, but it's quite out there, and someone will have to really scream loudly.
So I see Jackie's hand up, so maybe we can just, in the interest of time, make sure we get to hear from all the voices. So Jackie?
Yeah, sorry, I think this has been kind of addressed a little bit, but why does biophysics exist more in physics departments than in biology departments? Why are we a bunch of physicists talking about this rather than biologists?
That's a great question. Who wants to tackle it?
This is the American Physical Society. This is a self-selected audience. You have to understand that.
May I say something?
Mhm.
So in the Biophysical Society, we have a community of biophysics educators, and we all come from standard departments: physics, chemistry, biology, engineering, and we get together and we have this type of discussions. But it is in this other professional community in which, by the nature of the science, you have people from different departments.
Yeah, Raghu.
Yeah, I think that's a great question. I think there's probably many facets to the answer, but I do think that one of them is that one of the things this audience, like we all mean by biophysics, is not just taking a physical perspective on living processes, but doing things quantitatively and like with math. And many of my biological colleagues kind of lament the fact that biology education, including in many cases their own education, doesn't emphasize math, doesn't emphasize quantitative skills. And so that's kind of, in a way, an opportunity for physics, but it has led to this sort of a distinction. Oh, let me also add, since we are pointing out the flaws of physics education, of which there are many, one thing it does at least do well that many of my biology colleagues are rather jealous of is that you can't go through it without getting some not just proficiency but comfort with math. That's very hard to acquire later if you didn't have it during your education.
Yeah, that's sort of my understanding as well, is that math seems to be the difference between kind of like whether or not a biologist is wanting to talk about biophysics versus a physicist talking about biophysics. So I didn't know if there were other distinctions.
There are experimental skills that at least some schools teach their physics majors, or some proportion of their physics majors, that really are not taught in the biological sciences traditionally. Building equipment of any kind is not part of the standard biology undergrad, junior lab if they had one, but it is part of the physics one. So I think that's another sort of set of orthogonal skills. In physics, we have the whole experiment theory separation, but there is a tradition of doing experiments by building new kinds of physical tools. And that is something that we give at least the experimentally inclined colleagues or students that we have in our departments. And I also think as an experimentalist that's very important.
I think there's another thing, which is the quantitative things, but where you never do more complicated math than arithmetic, right? And that there's an awful lot that one can do. And just, I felt I had a big success on with one of my first biology collaborators, Tim Mitchison, was when he asked at a seminar, well, what sets the length scale? And the guy said to me afterwards that he never would have got to that sort of without having talked to physicists. There's an awful lot of this sort of quantitative thinking that one doesn't need any background to do. The physicists tend not to learn it that much. Some do, but not not all, and is another way to introduce things in the biology.
Great. All right. I think we could probably spend hours more here, and it's too bad we're not gathered in person and could just like head off for a relaxing drink and a more informal discussion. But this is the nature of the online world, which has its benefits because it's brought us all together from different parts of at least this continent. Please join me in thanking our three panelists for a fantastic exchange of ideas. And thank you all very much for your engagement in the topic. It's really always fun to gather for these discussions, and let's see if we can make something come of it around the idea of sharing resources. And yeah, reach out if you'd like to be involved in that, and we'll try to figure out a way to make it happen. And hope to see at least those of you who are at primarily undergrad institutions at next month's event. And if you're not interested in joining that event, stay tuned for our future events in this series. Bye, everyone.